Yep. Okay, so second half of 10.4. We are finding relative minima and maxima. And all that means is we are finding high points and low points in a graph. Okay? And so I can have a graph that has a lot of turns going on in it. And it is known as relative minima and maxima, relative maxima, because it's just a turning point and it's a high point relative to the location that it's in. It is not what I call the absolute high or absolute low. It's just a turning point. So I have these little positions all over here that make up my relative extrema. Mins and maxes, relative extrema. They are extreme values. These are, again, referred to as relative extrema. And that's, again, extreme values. High points, low points in the graph. Well, we talked yesterday about when the derivative is 0, right? When is the derivative of a function equal to 0?
Positive. When it's 0. When it's negative.
When the slope of the tangent line is 0. And when is the slope of the tangent line 0? When we have a turning point, a change in direction. Yeah. So at these locations, at all of these locations, f prime is equal to 0. So what I'm saying is that at the high points and low points in my graph, I will find a derivative equal to 0. And the derivative will only equal 0 at those locations. So if I take my first derivative and I set it equal to 0, I should be able to find all of the high points and low points in the graph. So I'm going to start by doing that. dy dx is negative 2x plus 2. So all I did was found my first derivative. That's the slope of the tangent line, and that's the general slope of the tangent line for this upside down parabola. So what I need to figure out is when is that upside down parabola changing direction? When does it equal 0? So the easiest way to figure that out is to just set it equal to 0, and then I can find when it's 0. And so to solve that, I subtract 2, and then I divide by negative 2, and I do end up with what I call my relative extrema at 1. Now I need to figure out whether it's a max or a min. And it's a very simple technique. Some of the graphs you can tell by looking at it, like I know right away, I just know because I've been doing math for many years, that this is an upside down parabola. I already mentioned it. It looks like this, right? So if it looks like this, it's going to change direction at its top, at a high point. That makes it a maximum. Okay. But some of them are not as easy to find. And so I do a little f prime chart. I'm going to call it here a y prime chart because we started with y. And what I do in a y prime chart, and we've kind of done math like this before, it's sort of like easy-ish math. Like I don't really think about what the values are exactly other than what their signs are, because that's important. Remember, this graph is increasing when the slopes are positive, and it is decreasing when the slopes are negative. And so what I need to do is figure out what's happening to the left and to the right of 1. Are my slopes positive or are they negative? If they're positive, it's increasing. If they're negative, it's decreasing. And I'm checking the derivative. This is what I'm interested in checking. So I'm going to do some quick math, and all I do is pick a test point. I'm going to pick a point to the left of 1. So can somebody give me a point to the left of 1? 0. Great. 0 is a great one. So I'm going to check x equals 0 in the y prime equation. Because I want to know at 0, does it come out positive? So I plug in 0, negative 2 times 0 plus 2, and I end up with positive 2. All I really care about is the fact that it's positive. And so this is what I call a positive region of the graph. Now we chose 0, but you would get the same result if you chose 0.9. You would get the same result if you chose 1/2. You would get the same result if you chose negative 10, which is why I put a whole bunch of positives. 1 is the only place that this graph changes direction, and we found that. It's not going to change direction anywhere else, so everything to the left of 1 is always increasing. Okay? I'm positive about that. And so what I envision in this graph is that it's increasing there. So I just draw a little kind of picture. Now I'm going to try a test location to the right of 1. And again, you can pick anything you want. If you feel like being, yeah, you could do the square root of 2, 5, 10, 100, 2. It doesn't matter. We're just going to pick one. I'm going to find y prime when x is 2. We'll just go with that, 2. Negative 2 times 2 plus 2. Again, I don't care what the answer is. All I care about is that if I do a negative 4 plus a positive 2, I'm going to get a negative result. So I don't have to plug it in my calculator. I just have to figure out what kind of result I'm getting. And that means any value to the right of 1 is negative. That means the graph changes direction at 1 and then is decreasing. And just by looking at what happened here, I can tell that 1 has to be a max. Okay? And so I say there is a max at 1 comma. Now I have to figure out what value that happens. This is where people get a little bit mixed up because we've been using the derivative to figure out the slopes. But I want to actually find the value of the point at that location. And so I have to go back up to this original guy here and plug that in. This is found when y has 1 put in it. The actual y function, the original y. So I'm going to evaluate y when x is 1.
For everything?
What's that?
For like everything?
Yeah.
X is 1.
So it's the opposite of 1 squared plus 2 times 1 minus 1. And that is actually, yes, 0. So I have a max at 1, 0.
Plug it into the derivative.
You plug it into the original. This is the original. Yep. When I'm doing this, I go into the original. This is the derivative. When I'm checking what's happening, I use the derivative. And that's the one thing that sometimes people get mixed up. Oh, where do I plug it into where? Yes.
When you plug it in there, like, how does it 0? Or where does it get the 0 from?
I took 1 and plugged it into the original y function, the one that was given up at the top. And it's the opposite of 1 squared, which is negative 1. Negative 1 plus 2 is 1. 1 minus 1 is 0. So I just evaluated that. Okay? All right. Okay, so let's go on and do our next one. Yes?
So you don't have to draw that little graph and everything?
I want you to draw this, but you don't have to do this. In fact, in our next one, we're not going to do this. Okay?
You have to draw that?
Yep, I want you to draw that. I'm not going to skip 6 forever, but I'm going to skip 6 only for now because I want to go down to another polynomial function before we get into a rational function. Okay? So here's my polynomial function. This is a cubed function. And again, I know what a cubed function looks like. Okay? It goes up and then down and then turns back up again. We've got those 3 moves. Actually, some cubed functions are just kind of a twist in the graph. I don't know what this one is, but I do know that I need to find my maxes and my mins by taking my first derivative and setting it equal to 0. So I found my derivative. I'm going to set it equal to 0. Can I factor out anything? I don't think so.
You gotta be able to.
I don't think 28, nothing comes out of 28. So I'm just going to factor this however I need to.
That's what I'm saying.
I'm going to break that down. So let's, we can snowflake it or guess and check or whatever works for you. It doesn't matter. It's 180 on top
So,
and 28 on the bottom. And this is 3x and 3x. And anybody think they found it? 10 and 18, nice. Yep. Yeah, however you, again, if you're like, I don't need a snowflake, fine. I sometimes don't too. Don't forget to reduce one side. That's an important part. So I get 3x plus 10 on one thing and x plus 6 on the other thing. How do I solve this equation? I do. I set both of those things equal to 0. So 3x plus 10 is 0, and x plus 6 is 0, and 3x plus 10 is 0 when x equals negative 10/3. Does anybody agree with me? Do we feel okay? Okay, good. Yeah, because I subtracted 10, I divided by 3. We're beyond algebra. We don't have to show all of those steps anymore. And then I have this other one at negative 6. Do we agree with that? Okay, good. So now I'm going to make what I call a y prime chart. You can call it a dy dx chart. You can call it an f prime chart, whatever your function is, but it's a derivative chart. And again, this is something that you do need to do. I need to see this. I'm going to put these numbers on this derivative. Don't put them in order that you solved them. Put them in order of value. Which is smaller, negative 10/3 or negative 6? Negative 6. So negative 6 goes here. Negative 10/3 goes here. Now I need to do little test locations. When I do my test locations, I do them in the derivative, and I usually use the most factored form. So I'm going to do my test locations in my derivative, and I'm going to start by picking something that is to the left of negative 6. So I need a number, any number, it doesn't matter which one. You said negative 7? Okay. I don't typically write down what I'm writing down now, but this is me doing y prime at x equals negative 7. And when I do that, y prime at x equals negative 7, if I plug negative 7 into here, I get negative 21 plus 10, which is a negative value. And then when I plug negative 7 into here, I get negative 7 plus 1, which is also a negative value. And a negative times a negative is a? So that means this region is all positive. And if you picked any other number that was other than negative 7 that was still to the left of negative 6, you would get the same result. Now I need to pick a number between negative 6 and negative 10/3.
Negative 5.
Negative 5, negative 4. Which should we use? Does it matter?
It'll all get the same.
Yeah, it'll all get the same answer. So y prime at x equals, I'm just going to go with negative 4. No particular reason. Again, I have those parentheses, so I'm going to do those little test points, and I'm going to plug negative 4 into this, and then I'm going to figure out what I get. So when I plug in negative 4 into the first, I get negative 12 plus 10. That's going to be negative 2. All I care is that it's negative. And when I plug negative 4 into the second, that is negative 4 plus 6. I'm going to get a positive, and I know my result is negative. So far, my graph is going increasing, changes direction at negative 6, to decreasing, and now I want to see what's going to happen at negative 10/3. And so I'm going to pick a test point that is to the right of negative 10/3, any number.
Can you plug in 0?
You can. Is it to the right of negative 10/3? And then it will work. So I'm going to do y prime when x is 0. I always try to pick the easiest number to work with. When I plug in 0 in the first parenthesis, I get a positive value. When I plug 0 in the second parenthesis, I get a positive value, which means this is a positive region, which means that this is increasing. So just looking at the little picture that I drew, again, you don't need to write this part down. This is something that I typically just do in my head, okay? I just do my test point, I check it in the thing, I don't write it down, and we'll get to problems where we don't write it down as well. But this is my test points. Once I get my result, I need to read this. I need to be able to understand what this is saying. If it's increasing and then decreasing, -6 must be up. I'm increasing and then decreasing, -6 must be up. Max. And then if I'm decreasing then increasing after that, -10/3 must be a min. So I say I have, I'll tell you, I say that I have a max at -6 comma something. I'll figure out that something in just a bit. Yep. And I have a min, oops, pretend I spelled that right, at -10/3 something. And this is where I take out my calculator and I have to figure these out. I have to plug these into the y function. I'm plugging it into this original. I'm going all the way back down here to solve these, okay? Plugging it in. And this is where my calculator comes in very handy. I'm going to evaluate y when x is -6, and that is -6 cubed plus 14 times -6 squared plus 60 times -6 plus 76. Yeah, that's a little icky ugly.
But I know how to do it.
Good, yeah, you're just plugging it in. So let's see if some people can plug those in and get us a value. 4. Does anybody agree with that? Okay, great. So that's 4. And now I'm going to do the other one, y, when x is -10/3, and I'm going to go through the same process. Again, this is in my original, -10/3 cubed plus 14 times -10/3 squared plus 60 times -10/3 plus 76. Okay?
-148 over 27.
Okay. Which is about, well, which is exactly -5 and what?
1 sec. Let me switch these. 1327.
Oh, no, that is mine.
Yeah, yeah. So you could get it in many different forms. You might have even gotten -5 point something, depending on how you plug it in your calculator. So you could have any variation of that. I don't care if you put decimals down. Okay. All right. I do want to go back up to our rational function now. It's a little bit scary, but, okay, a little bit scary. However, what we do, the process that we follow doesn't change. I want to find where I have maxes and mins. I want to find where there's relative extrema. I find that when the first derivative equals 0. I find that when the slope of the tangent line is 0. I find that by taking the derivative, differentiating this function, those all mean the same thing. And so this is a quotient, dy dx is low d high minus high d low over low low. Okay. It is a little bit intimidating when I look at this first, because it's like, man, I'm going to set this equal to 0 and solve this? Yeah, it's not so bad. Yeah.
Are we able to like simplify it down before?
Yep. So I'm going to set this equal to 0, and then I'm going to distribute that on the top, so that's 6x squared plus 12x minus 3x squared. Yes, it is. Thank you. Over low, low. Okay, so there I am right there. I can still combine that 6x squared minus that 3x. And I'm going to do those, I'm going to do two things at once. One thing I'm going to do is get rid of that denominator, or move that denominator out. And how do I move the denominator out? I multiply it. Yep, so I'm going to multiply both sides by that denominator, 3x plus 6 squared. So 3x plus 6 squared. On the right, it just cancels out. That was my whole point of doing it. On the left, what happens?
Oh, 0.
It's 0, yeah, because anything times 0 is 0. So as scary as that was, it really came down to now this, 3x squared plus 12x. That's not bad, that's doable, right?
Oh, whoa.
I did the 6x squared minus 3x squared right away. The numerator. Are we okay? I got a whoa, and then, yeah.
Can you just divide the rest of the equation by that too, so that then you do 0 this one?
Can I what?
Never mind.
Just read up.
Yeah.
Okay.
So you're okay with this, right? That made 0, okay? And then all I did was combine these like terms.
It's illegal. You have to at least multiply every
6x.
Don't you have to multiply by the top
Can't
though?
find
No, the bottom and the top cancel each other out. That's the whole point of doing that,
Over 1.
to get it out of there. Yeah.
Okay, how do you factor that? How do you factor that? So the bottom just disappears?
Yeah.
Without adding anything to the top?
Correct, yeah. It cancels itself out, yeah. And as long as I do the same thing with both sides. You've done this before, right? So I'm just gonna go on like old school. X over 3 equals 10. How do you get rid of the 3 in the denominator? You multiply by 3. What happens to it? Oh, it disappears. Same thing, just on a larger scale, as long as I do it on both sides.
3 goes to the top.
What's that?
I thought the 3 goes.
No, it cancels the bottom out.
No, because.
What?
I think you. Does it every. Never mind.
It goes to the other side.
But the other side's 0.
Yeah, but for us, because the other side is 0, it turns out to be 0. So we just get to multiply it out, and it's like it's not even there, pretty much. Okay,
I know you.
now, how do I factor this?
Yeah, that's kind of messed up factor.
Oops. It wasn't that messed up.
Oh, I thought you had to do it.
Yeah. So I pulled out a 3x. 3x times x was 4. And then I'm going to set my things equal to 0. 3x equals 0. X plus 4 equals 0. So my extrema happen when x is 0 and when x is negative 4. That's when my extreme values happen.
Are we not doing number 8?
I
need some extra space.
Do you? I'm sorry. Yeah, I should make more room on these.
We don't got to do number 8.
We probably don't have to do number 8.
I was gonna say,
Yeah.
we've already done 2 of those.
Okay,
same
yeah.
equations, so I
Okay,
think we're-
and we're going to do the other ones anyways too, so it's kind of the same thing. It follows a similar pattern. All right, so I'm fair with that. I can make that. So let's scribble out 8 for now. We'll revisit something like that later, and then you can blend your work into that spot. So I'm going to make my y prime chart or my dy dx chart. I put them in order from least to greatest, and then I do my test points as well. So I want to test something to the left of negative 4. Negative 5. So when I plug in negative 5 here, I get a, times 3, I get a negative. I'm gonna write it under here. I get a negative, and when I plug negative 5 into the next one, I get a negative, and a negative times a negative is a positive. So that region is positive. So all I did is plug in my test points. Now I'm going to do the next. When I plug in something between negative 4 and 0, I get, or I can use 2. Let's use 2. Negative 2, you mean?
Yeah.
Negative 2? Okay, so we're going to use negative 2. So what do I get when I plug in negative 2 times 3? Negative. Yep. And then negative 2 plus 4, positive. That means that's a negative region. Now here's where, again, I'm not showing where I did over in these last two. I did the actual math. I showed you what I was doing, plugged it in. You don't need to do that. You can just talk yourself through it as long as you make sure that you are using the derivative when you are making that table. That's what you're plugging it into the derivative when you're making that table. Otherwise, things are going to get a little bit funky. So now I'm going to do the last part. I need to pick a value that is to the right of 0, and that is 1. And so I'll pick positive 1, and when I put a positive 1 in here, I get a positive. And when I put positive 1 in here, I get another positive, and that is a positive region. So again, if I am increasing up to -4, and then decreasing, -4 is a max. And then if I'm decreasing up to 0 and then increasing, 0 is a min. You just envision what's going on with those slopes. So I finish this off by saying I have a max at -4, comma, something. And I have a min at 0, comma, something. And I have to use my original function. I'm bringing that down here to figure out when that is. Original function way up at the top. Yes.
I don't understand how you decide in terms of max and terms of
So if I again envision that's what these help me find. So I am rising and then dropping.
Oh, it's 0, 0?
When you rise and then drop, you hit a high peak. So there's a high peak at -4.
So it's not a parabola.
This is not a parabola, no.
But
Yeah.
the power too.
That doesn't matter, it's got a denominator and that changes everything. Are you okay with that now? Does that make sense? So again, this is rising and then dropping and then rising again. That's not what the graph looks like, but that's what's happening. So I have a high point at -4. All right. So this is y when x is -4 is -4 squared over 3 times -4 plus 6. And that looks like 16 over -6 or -8/3. Or fraction decimal equivalent to that if you plugged in your calculator, whatever. I'm just, again, doing the math. And then I'm going to evaluate this next one. Y when x is 0. And again, this is y. I use the y function. 0 squared over 3 times 0 plus 6. That gives me 0 over 6. That gives me 0. So min at 0, 0.
I got it right.
Did you? Good. Excellent. Excellent. Okay. So, again, I say these notes tie in very closely with the next notes with 10-5. And so we'll do a couple of 10-5 today as well. Just a couple. We're not going to do them all. And then we'll come back and kind of review, okay? Tomorrow we'll start off with a review. So here's 10-5. 10-5 is a point of inflection. So in a graph, not only do I have extrema, so if I just graph a curved function, and I'm just going to graph sort of a cubed function, okay? In a cubed function, I have a max, I have a min, agreed? A high point and a low point. Those are my relative extrema. I also have a point of inflection. And the point of inflection is the exact location that this graph changes from concave down to concave up. And so my point of inflection is somewhere in here.
Oh, just somewhere in the middle.
Yep. How do you find that point of inflection, where it changes concavity, where it goes from concave down opening down to concave up. That happens when the second derivative equals 0. So f prime of x equals 0 at mins and maxes. F double prime of x equals 0 at a point of inflection. POI, point of inflection, and that is where it changes concavity. So this, again, that point of inflection is summed up as where the graph changes concavity. Okay, that's what a point of inflection is, where the graph changes concavity. Again, I hope that makes sense. Concave down, it's opening down, and then it flips this location and it opens back up. And all of these things are very useful when we get into graphing our shapes. And that is actually what we do in our next chapter, graphing. Okay, a lot of graphing. So, what the heck is a second derivative?
You know, you just multiply by 2.
No.
You square it.
Isn't
No.
that explosive?
Oh, you add them together and divide by 2?
No.
What are we doing?
So a second derivative
But derivative
is
is derivative.
exactly as it sounds. Yeah, you take the derivative of the derivative, that's it.
There's no way that's real.
That is for real. Yep. Okay. So here we go. Second derivative.
Wait, just wait.
Yes.
Our shortcuts still work for these?
Absolutely. Yeah,
Okay.
absolutely. F prime of x is 3x squared minus 6x. That is the first derivative, which is the slope of the tangent line. And again, that's when that equals 0. I can find when I'm changing directions because that's when the slope would be 0. F double prime of x is the derivative of the derivative, 6x minus 6. That is the second derivative. Yep.
What's the definition of the second derivative?
So it depends. It represents multiple things. So in physics especially, it is the first derivative is velocity, the second derivative is acceleration. The third derivative is jerk. So if you ever get into physics, you'll talk about those kinds of things. But for us, the first derivative for what we're doing, the first derivative gives us our extrema, and the second derivative gives us change in concavity. So that's it. That's all. But there are different uses for it depending on the subject or the topic at hand. Okay? Okay. So just like before, I'm going to set it equal to 0. You never know.
No, I know.
Yeah.
So in
I
this
am sorry.
chapter, we're just learning, or just using the second derivative. We don't need to worry about the
A
first
third. Oh, yeah. In this section, all we care about is the second
one.
derivative.
I'm
Yeah.
sorry, the third?
The third, we won't do the third. Yeah, but you will. if
We're
you-
skipping the third.
We're skipping the third, going straight. No.
Is the third derivative the derivative of
The derivative of the derivative, yeah.
So it would just be.
And you can do it, honestly, I can keep taking derivatives until it gets to 0. And if I'm taking derivatives of sine and cosine, I can take derivatives endlessly. Because the derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, and I can keep going forever and ever and ever, and never stop.
Oh, never
And there's
mind.
an application for that as well. All right, so I need to make an F double prime chart. But remember,
Oh, it's just one.
the first derivative gives me mins and maxes. The second derivative gives me concavity. I interpret it different. I do it the same way. I interpret it differently. Okay? So my second derivative was 0 at 1. And then I'm going to do a test point. I'm going to evaluate f double prime at x equal to 0, say for instance. And that would be 6 times 0 minus 6, which is a negative 6. All I care about is that that's negative. Negative means concave down. okay? Negative tells me right here, this does not mean decreasing anymore. This means concave down. Squeeze that in. What is concave down? Concave down means, looks like that. Opens down. Okay? Now I want to do the same thing, but I'm going to do my test point in the other region, F double prime, when X is, I don't know, 2.
So it's just positive. So it's a concave up.
And so that is a positive region, and that is concave up. Yep. Yep.
What is that called?
And so concave up is, like that. And if I put this together, if I slide those two things together, it means that this graph is going concave down. It hits its point of inflection at x equals 1. And then it's concave up, and it finishes the rest of its journey. That's what it's telling me is going on. Now, somewhere on the other side of 1, there is a max, and somewhere on the right side of 1, there is a min, but that's found with the first derivative, and we're not doing that in this section. Okay, we did that in the last section. Yep.
So like this whole thing about
Yep.
intervals of concavity.
Yep.
That's
Yep.
just the concave down, concave
Yep. So this is how I write my intervals of concavity. To the left of 1, if I keep moving left and keep moving left and keep moving left, I will go to negative infinity. Negative infinity is over there, right? And so from negative infinity up to 1, from negative infinity up to 1, this graph is concave down. That's how I answer this. That is my solution to this. Because to the left of 1 is all of the negatives. And it doesn't matter what negative number I plug in here, it's going to end up with a negative region, which means that's all part of the concave down region. And it goes all the way to the start of our numbers on the negative side, and that's negative infinity. So on the other side, it's going to go to positive infinity. Yeah. So then I do, on the other side of 1, up until positive infinity, this is concave up. And that's what my answer looks like for these. Again, let's do one more. And then I'll give you a handful of problems to try tonight for homework, and then we'll practice a little bit more tomorrow.
No,
Okay, you said no? No? Okay.
handful?
A handful.
How many is that?
I don't know, like 4 maybe.
I think I can only fit one.
F prime. 4x cubed minus 8x. Are you guys getting fast at deriving? Pretty fast. F double prime. 12x squared minus 8.
Whoa.
I took the derivative of the derivative. And now I'm going to set it equal to 0. I can't really factor that. I don't see what I can factor out of that. So what I'm going to do instead is I'm going to add 8, divide by 12, simplify that, take the square root, blah, blah, blah. Yes.
What?
That's
it?
I could. Sure. Sure.
Did
It
you
could.
get this equals 0?
Should we do it that way? Pull out the 4? Okay.
Yeah, that's what I did.
So 0 equals 4 times
Factor out the 8.
3x squared minus 2. Good? Okay? Still, it's not a nice factorable one.
That's beautiful.
It's not terrible, but it's not nice.
Oh, I do.
So I'm going to set my factors equal to 0. Well, 4 will never equal 0, so non-issue. 3x squared minus 2 will equal 0 when I add 2 and divide by 3, and then take the square root of both sides. Here is a mistake that is going to happen over and over and over again, and I wish that I could make it not happen. But please, please, please try to remember when you take the square root of a number, it is plus or minus. When you take the square root of a number, it's plus or minus, which means that I have actually 2 locations where this changes concavity. And if I think about it, it should make sense because this is a 4th power graph, and on a 4th power graph, they sort of look like this. Right? Does that look familiar to your 4th power days? It's got a change in concavity on each side of those min, max, min locations. Okay? All right, I'm going to just real quickly rationalize my denominator. So this is plus or minus the square root of 6 over 3. Are you guys okay with that?
I don't know.
Good. What the heck did she do? I remember that this is the same as the square root of 2 over the square root of 3, and I'll multiply the square root of 3 on the top and on the bottom. Good? Make sense? Okay. That's kind of an ugly number, but we don't judge. I'm just going to go right in. I'm just going to jump into my little table, and I'm going to make my F double prime chart. And the negative square root of 6 over 3 is here, and the positive square root of 6 over 3 is here. And when I pick my values, I want to just kind of pick places that I know are on the other side. Sometimes I'm going to have to pick a decimal if they're really close to each other, and that happens. But sometimes I do things like, I know this is, square root of 6 is between 2 and 3, so I know that this number is like between 2/3 and 1, negative 2/3 and 1, okay? And so I could pick -1, I could pick -2, I could pick -10. If I'm not sure, I just pick way over on the side. I pick a big number that I know it's out of it, okay? So we're going to choose -2. So I'm going to solve f double prime when x is -2, and again, it goes into the double prime. And so that is 4 times 3 times -2 squared minus 2. And again, I just have to sort of envision what's happening. It's definitely positive, right? Yeah. Because this would be positive 12 minus 2 is 10, 40. So this is a positive region. And again, that means concave up. That's how I interpret it. I don't interpret it as mins and maxes. Yeah. And then between a negative and positive number is always 0. So I'm going to do f double prime when x is 0, and that is 4 times 3 times 0 squared minus 2, and that becomes 4 times -2, or negative, concave down. Okay? Then I'll do something on the other side of that, something like 2. And that's 4 times 3 times 2 squared minus 2. And again, that comes out to be positive, so it is concave up again.
Okay, so what do we do next?
Okay? Now we interpret it.
Enter.
Yep. So I know on this side of the graph is negative infinity, right? And on this side of the graph is positive infinity. And so I'm just going to write my interval. I have 2 concave ups. So it is from negative infinity up until negative square root of 6 over 3. It is concave up. I don't care if you abbreviate. And then from negative square root of 6 over 3 up to positive square root of 6 over 3, it is concave down. And then, from the square root of 6 over 3 up to positive infinity, it is concave up again. And that's my answer, yep. So don't overthink how you interpret it. You interpret it exactly as it kind of appears there. Okay, bam, bam, bam. That was a lot of me talking, a lot of notes. A lot of stuff to think about. First derivatives, second derivatives, how I treat them differently. So what should we do for homework? Let's do, let me stop this maybe. In your homework.